Okay, today I'm going to talk about integrating the function e to the x. Before I do, I want to just do a little bit of review. This should all be coming back. This should all be familiar to you from either from pre-calc or from earlier in the year. So first thing is, do you remember what this little -1 here means? Hopefully you recognize that as being the inverse, and that when you plug the inverse into the original function, all that happens is they cancel one another out and we get x back. Or if I put the original function into the inverse function, again, they undo one another and all I get back is x. So if I ask myself, ln of what number gives me x back? So in other words, what's the inverse of the natural logarithm? Well, the inverse of the natural logarithm is our natural exponential function, e to the x. And whenever I take f inverse of ln of x, I get e to the x. Or ln of f inverse, I get e to the x. So again, ln of e to the x equals x because they are inverses, and e to the ln of x equals x because they are inverses. So what does the graph of e to the x look like? Well, remember, it's just a specific type of exponential function, and it is exponential growth since e is about 2.78, and it passes through the y-intercept of y equals 1, and it looks something like that, and it'll continue to go up if I were to extend it. Next thing I want to review is the derivative of the natural exponential function. So the derivative of e to the x, remember, is just e to the x. If e is being raised to some expression, say we call that expression u, then remember that e to the u is just e to the u times du dx. So in other words, e to the u times u prime. So it's a form of that chain rule. So looking at a couple differentiating examples, if you want, you could pause the video to see how well you remember these, since we did do these a while ago now. On the first example, I noticed that it is a composite function. I do have that top function of 2x, so if I wanted to, I could say u equals 2x minus 1, and v equals e to the u prime equals 2, v prime equals e to the u. So the derivative of e to the 2x minus 1 equals u prime times v prime, and 2x minus 1 gets put back in place. So notice I did get the derivative of u times e to the u. If I look at the next one, I have the same situation going on where I have that composite function, where I have this upper function here, and then my natural exponential function. So again, I'm going to go ahead and let u equal my top function, which is -3 over x, which for differentiating purposes I'm going to write as -3 x to the -1, v equals e to the u prime. It looks like I didn't need to write that as -3x to the -1, because now looking closer at it, I realize that is just -3 ln +3 x to the -2. And I use my differentiating rules. And v just stays e to the u. So the derivative of e to the -3x becomes u prime times v prime, which is 3x e to the -3 over x. Kind of a sloppy 3 there. So there's the review. So now if we look at some new stuff, we have this new theorem that tells us the integral of e to the x dx is still just e to the x plus c. If you think about integrating and differentiating are inverses of one another, so the derivative, when I integrate a function, I just get back what the function was before it was differentiated. So what was e to the x before it was differentiated? It was e to the x, and then of course that plus constant that may or may not have been there. So oftentimes we still have to use U-Substitution when we're integrating exponential function. So let's say, for example, I have the integral of e to the 3x plus 1. I would let u equal 3x plus 1, and then du dx would equal 3. So du would equal 3 dx, and I notice that I have the dx. All I'm missing is the 3. We've had quite a bit of practice with this now, so I just rewrite that as 1/3 3 e to the 3x plus 1 dx, and now I'm able to substitute du in for the 3dx, giving me 1/3 times the integral of e to the u du, and then I can see right up here that the integral of e to the u is just going to be e to the u plus c, so I get 1/3 e to the, and then I'm going to put 3x plus 1 back in for u plus c. If I look at my next example, so very similar. I'm going to go ahead and try u substitution to begin with, and I'm going to let u equal negative x squared, and then du dx equals negative 2x. So I see that I have this extra 5 that I don't need. I can bring that to the front. I'm also missing a negative 2, so I can put a negative 2 in by pulling out a negative 1/2 out front. So I'm going to rewrite this as negative 1/2 times 5 times the integral of negative 2 x e to the negative x squared dx, which is the same thing as negative 5/2 times the integral of the e to the u du, which gives me negative 5/2 e to the u, which is e to the negative x squared, plus c as my final answer. I think that is the last of the example. Oh, there is one more. So looking at the third example here, I'm going to go ahead and try to integrate this. This might be a good one if you want to try one on your own. This would be a good one to try. I'm going to go ahead and say that u is cosine of x, and then the derivative of u with respect to x is negative sine x. Well, look at what I have. Du equals negative sine x dx, and I have the sine x and the dx. I just need the negative. So I'm going to go ahead and put a negative out front and a negative inside. And then I can say, well then, that is negative integral e to the u du, replacing negative sine x dx with du. And I get the integral of e to the u is back to e to the u, so the negative drops down. I put cosine of x back in for u, and I add my plus c. And there's my integration. That is all you need to do to integrate e to the x. If you have any questions, bring them in with you to class tomorrow.